Swayam Prabha. Digital India. Educated India.
Hello all, welcome to Astrochemistry. This is lecture number 74 and this is also tutorial 20. So in the last lecture, that is lecture 73 and tutorial 19, we were discussing about various aspects of astronomy as pertinent to astrochemistry. If I'm correct, we were discussing about the notions of how to obtain column densities and number densities using the idea of line of sight. So that is what we discussed in the last tutorial. In this tutorial, we shall be continuing with some more astronomical aspects important for astrochemistry. Now, the first question for today's tutorial is going to be, what are and spectral resolution in astronomy? And of course, what is the relevance in astrochemistry? What is their relevance to astrochemistry? So this is the first question we shall be tackling. The answer is, now your spatial resolution. Okay, I'll begin with the spatial resolution part first. So spatial resolution is a measure of how well you could distinguish between any two astronomical objects. Astronomical light emitting sources. Okay, so it's a measure of, let's say, I'll give you an example. You, on a cloudy day, right? You look at some hilltops, okay? You think that there is only one peak from a distance. But then, as you go closer, right? You realize that, there actually are two peaks, right? So the two peaks are going to be the two sources. In this particular case, two light emitting astronomical sources. So how well are you able to distinguish between any two different objects lying at a distance? So that is the idea of spatial resolution. And it is actually measured typically in, this is measured in terms of, it's an angle that is going to be a parameter to understand spatial resolution, expressed as an angle. So this is typically expressed as an angle, and either in degrees or radians or in arc seconds. So pi radians is equal to 180 degrees, and we also have like this measure in arc seconds. Okay, so the arc second is going to be approximately 1/60 square degrees. 1 arc sec. So this is how the connection between arc sec and degrees is established. Okay, so what sort of an angle are we talking about? Let's say that this is an observer. For the sake of simplicity, I'm representing it as a point, but typically you can think about it as the center of a lens as part of a telescope, or if you're viewing anything with your naked eye, you can call it the center of your pupil, etc. Okay, this is the observer, represented by this point here. And let's say that, there is one source S1 here and S2 here, right? And light is coming from S1 and S2 both. So this angle theta is a measure of your spatial resolution. Okay, so theta is a measure of spatial resolution. The minimum resolving angle, that is, there needs to be a minimum angle via which S1 and S2 might be separated. Okay, if like the separation lies within the angle, then you may not even be able to distinguish between the two objects. The minimum angle, it might not be possible to resolve between S1 and S2, which have two astronomical sources, is given by, if we are considering, in arc seconds, that is going to be 250,000 lambda divided by d, where lambda, right, is the wavelength of the radiation, and your d is the distance between the two sources. Okay, is the distance between so d is the distance between S1 and S2. All right, so this is what is given by theta. This is in terms of arc seconds. Okay, please note it. Theta in, of course, you can convert it to radians. Once you convert it to radians, the number is going to be given by, I think, 1.22. That's the number. Okay, and note that, see, this is an angle, which means that both your lambda and d have to be in the same unit. Are we clear? So this is what is called as a spatial resolution. Just get to know the name right now, and that there is a formula associated with it. How is this derived? Well, so I'm not going to go through the details of its derivation because it involves solving what are called as complicated Bessel functions. One can do it, but it is going to take up a lot of time. We don't have the luxury because we have to cover other topics also in this course. Okay, so I'll just briefly tell you the broad principle behind how especially this prefactor is obtained. Okay, and I'll leave it at that. The prefactor, 250,000. Okay, right? Note, the prefactor comes about due to the math of the diffraction pattern obtained from the light. So, even though I've mentioned that this O is a point, it's not a point. It is more like it has an aperture, it has some fine edge, right? So once light reaches it, it gets diffracted. So the moment it gets diffracted, the dynamics of diffraction is given by what are called as Bessel functions. So this math is described by what are called as Bessel functions, and by using the Bessel functions, you can find that this number comes up naturally as distance between the first central maximum and the minimum, okay, and the next minimum. So that's how this number comes. Don't worry if you don't precisely get how exactly this is obtained. Take it for granted. It's very easy to perhaps take up any astrophysics or an astronomy textbook to get exactly how this number is obtained. In this course, we are avoiding giving further details. Okay, so note again that we intentionally skip further details. That's the whole point behind spatial resolution. In fact, to give you an example, this specific equation, I'll write the equation again over there. It's simple enough. Your theta equals 250,000 lambda by d, right? Now, using this, okay, let's say, you're simply viewing the moon with your naked eyes. I mean, everyone likes to see the moon, right? So using this, when you look at the moon with just the eyes, you see, you look at the moon from your eyes, you'll be looking at various features, right? We see that the moon is not completely white as it appears to our eyes. There are several dark spots. Together they form a pattern. So what are the spots? How far apart can, let's say, find structures in the moon, okay, right? So you have this formula. Using this, when you look at the moon with just the eyes, how far apart can finer features be resolved? Okay. In other words, the moon has various features, right? We see the dark spots. From when we look at them, we see that, okay, they're all a collection of spots put together. But in reality, they may be quite far away. Okay. So what is the minimum resolution that we can understand with our naked eyes when we look at the moon? That is the question. Okay. Now, to solve this problem, what data do you need? So the data that you need for this is, besides this formula, you're looking from your eyes, right? You need to know the diameter of your pupil. Okay, right? So the diameter of your pupil is roughly 1 millimeter. All right. Oh, hey, by the way, a small correction. This D, okay, right? This let's say, this is at some other distance, small d here. I apologize, there's a small mistake. The capital D here is not the distance between the two sources. Instead, your capital D is the diameter of the collection source. For example, thank God we know we did this example to spot this right away. So even though it is represented as a point, I would rather do it this way, right? Let's say it's like a lens. So the diameter of the lens, capital D here, is not the distance between S1 and S2. I stand corrected. That's a mistake. I'll correct it immediately in the lecture itself. Please note this. Okay. So capital D is the diameter of the collecting source. So what I've written is D is the diameter of the lens. Let's say that the lens is the receiver. So the collecting source or the receiver, so that has a finite diameter, right? That is what comes in the in the resolution formula, not the distance between the two entities themselves. Although as D is further and further, we can resolve it better. As D becomes smaller and smaller, that is the small d, that is the distance between S1 and S2 becomes smaller and smaller, we'll be having a more difficult job to resolve between the two entities. Please note this. Okay. So I stand corrected. The mistake I made was I used the formula, I gave it different, I assigned the parameter physical D with some other object. Okay, right? This is something small d. It is not part of the formula. The distance between the two sources, right? That is S1 and S2 is small d. That is not part of the formula for your, the minimum resolution. All right, please note this point. Okay, so the diameter of the pupil is roughly 1 millimeter. All right, And let's say that the wavelength, okay, say lambda is 500 nanometers. Okay, right? So that can always be, converted to meters and millimeters subsequently. All right. So then, using this, okay, right? Using this, your theta, you can calculate using this formula to be roughly 125 arcsec. Okay. So this 125 arcsec implies that the distance, that is the small distance, okay, right? The small d between the two sources, d between two sources is roughly around 200 kilometers. Okay. So once you get this angle, right, the small d you can obtain using some trigonometry. Okay, that's not a problem. So in other words, when you see the moon with your naked eye, so if you're able to see, two distinct features, they're actually 200 kilometers apart. That is what this formula tells us. Okay, please note this carefully. This is the case with simply, like looking at the moon with our naked eyes. So for modern telescopes, typically, for telescopes, your theta, that is the minimum resolving, minimum resolution, should be of the order of at least 1 arc seconds or better. Okay, to achieve sufficient spatial resolution. Okay, so to achieve sufficient spatial resolution, your telescope's minimum resolution should correspond to at least 1 arc second or better, right? That's when you will be able to distinguish objects which are lying close enough, in the sky. All right, so please note this point. So this also tells you, if you've ever seen telescopes, they always talk about telescopes being, the bigger telescopes being better. Why is that? Because, larger the diameter, that is the capital D, right? Larger the capital D, you're at any given wavelength, using this formula, the minimum resolution is therefore going to be better. And that's why larger telescopes are preferred. Okay, so this is about spatial resolution. We'll now go back to the concept of spectral resolution. And I once again want to bring to your attention a small mistake I made, a small but important mistake I made. It is that this capital D over here in the formula for formula for the resolution, which is of course an angular resolution, the D is the diameter of the collection optics. Okay, right? So D is the diameter of any lens or any telescope of the human eye or something. It is not the distance, which is of course some other parameter. Okay, please note it. And I've not given you how we derive this formula. Please be clear about this. Okay. All right. I'll now finally move on to spectral resolution. So now, if you were to discuss about so what is spectral resolution? Spectral resolution is the, let's say, ability of any, let's say, a telescope or any optics, any receiver, okay, right? Any receiver of radiation from space, of, let's say, a telescope. I'll just put telescope as one example, okay? To resolve between any two wavelengths. See, so your spatial resolution talked about resolving between any two, the distance wise, right? Between any two objects at a given wavelength. So spatial resolution referred to resolving between objects that lie at a distance at a given wavelength. And your spectral resolution is about resolving between any two wavelengths of radiation. Okay. Now that's the distinction between spatial and spectral resolution. Now note this point carefully. When we discuss about spectral resolution, once again, the diffraction pattern for a just resolved or minimally resolved spectrum. Here I use the word spectrum in the sense that I talk about spectrum as a collection of wavelengths. So the diffraction pattern for a just resolved or minimally resolved spectrum should look like so. Let's say this is the intensity of the diffraction pattern, and this is the wavelength. So for one particular wavelength, so let's say that like this is lambda 1. Of course, this is I versus lambda, and this corresponds to lambda 1, and this corresponds to lambda 2. Now you can see that as the two different wavelengths, as the waves come further and further, they are easily resolved. But as they come closer and closer, they cannot be resolved at all. But there happens to be one minimum value, okay, right? Such that effectively, right, when the dip, let's call this like point, I'll call this is lambda 1. I'll call this point as A. This is B. This is C. This is D. And this is E. So please note that your AC is greater than DE. Okay, right? So your AC is greater than DE. So whenever, effectively what I'm talking about is, so you have two different peaks for the two different wavelengths. From the, plotting the intensity of the diffraction pattern. This is known from experiments. Okay, you can also write the formula for it using again the Bessel functions. Effectively, you can imagine that due to the curves being close enough, there is a dip being formed. There is a dip being formed between the two curves. So when the distance between your the dip as a resultant of both these, both these like curves coming to very close, the difference between your AC and DE, if AC minus DE is at least 19% of AC, then the two peaks, then lambda 1 and lambda 2 could be resolved. Please note this point, okay? This is what is called as the Rayleigh's criterion. This again also could be derived using the ideas of Bessel function and some, the basic Bragg's law associated with diffraction, but we won't go into that. But please note that there is a minimum resolution beyond which any two wavelengths can also not be further distinguished. Okay, so this is the spectral resolution. And where is this coming from? So this is actually coming from, note, spectral resolution is coming from your Bragg's law for diffraction pattern. So I'll just tell you where it is coming from. I won't go into the details. Okay. So we have now understood that there are two key important things as far as astronomy is concerned. We want to be able to distinguish between two objects that are further apart in space, and we also should be able to distinguish between any two wavelengths. Now, what is the relevance of both of these ideas in the context of astrochemistry? Well, it is simply that you should be able to understand what molecules are present in which part of the universe, correct? So therefore, you must be able to see and map precisely where the light is coming from which source is the light coming. So that is why spatial resolution is important. And likewise, of course, it becomes obvious that different molecules have different excitation wavelengths for any type of transition. It can be rotation, it can be vibration, or it can be electronic also. So it is natural to see that the distinction between any two wavelengths, that's extremely critical to distinguish between the different types of molecules that are present in space. So overall, these two aspects, spectral resolution and spatial resolution, they are vital, in astrochemistry also. So on that note, I end this lecture and I'll see you in the next lecture. Thanks a lot.